So, hello everyone, and welcome back again. We now enter the last for today's session of our summer school workshop, Quantum Horizons, Developments and Opportunity, where we will have another wonderful episode with Professor Jeremy Levy, a world-class expert in the field and a wonderful person. Jeremy Levy is a distinguished professor of condensed matter physics at the University of Pittsburgh and a founding director of the Pittsburgh Quantum Institute. He received an AB degree in physics from Harvard University and a PhD degree in physics from the University of California, Santa Barbara. His research interests center around the emerging field of oxide nanoelectronics, experimental and theoretical realization for quantum computation, semiconductor and oxide spintronics, quantum transport and nanoscale optics, and dynamical phenomena in oxide materials and films. Professor Jeremy Levy has kindly agreed to join us for this school, and he is going to give a great talk, Correlated Nanoelectronics and the Second Quantum Revolution. Jeremy, we are absolutely thrilled to have you with us. Please come and begin.
Well, thank you. Thank you very much. My regret really, of course, is not being able to join in person. We're still, I guess, re-emerging. And it was also some scheduling conflicts, but really delighted to be able to join for this summer school. I think these are great venues to have a relaxed learning various topics, and I'm really thrilled to be here and to join you. So I don't know how all the question stuff happens, whether it happens during the talk. I'm happy to address questions during the talk or afterwards. But I will probably just get started now and share my screen. So is this all visible?
Yes, it's perfect.
Great. So yeah, the title is Correlated Nanoelectronics and the Second Quantum Revolution. I'm going to give a little bit of sort of background and context to the the various fields that my research overlaps, and give an indication of where it may be going. I'll also say that I don't know if you're students or undergrads or graduate students, but we're always looking for great PhD students in our program. So quantum computing. Well, you could say that it has arrived, right? It is a thing now. How do we know? Well, we've got clip art, and so I think if you go into Microsoft and look for pictures of quantum computers, now there's like a thing that represents a quantum computer. We're still working on the emojis, but that's going to take a little bit longer. So stepping back, right? I mean, quantum computer is the thing. You can think about it, what it means, and we'll talk about it in a little bit. But the context is really much bigger and spans not only this century, but the previous century. And so, in the 20th century, we had the first quantum revolution, which was really the discovery of quantum mechanics and its application in so many different areas, whether it's going to explain the periodic table or provide the foundation for quantum description of light and lasers and all the technologies, telecommunication, computers, and so forth. Really, none of this would be possible without understanding this sort of operating system level of our universe. But quantum mechanics, as you all know, you're studying it, there are a lot of weird aspects of quantum mechanics that don't necessarily sort of fit into your personal technology directly, things related to quantum dynamics and quantum coherent states and so forth. These are also have the potential to develop new technologies like quantum computers, but also quantum sensors, quantum communication protocols, and so forth. And these, we're really at the beginning of our understanding of the range of possibilities that are that come from these leftover concepts, that entanglement and so forth, that we believe may be as impactful or more impactful than in the first quantum revolution. That's the thing about scientific and technological revolutions, is you don't necessarily know where things are going, and I think we're at that stage where we don't really appreciate. Maybe somebody out there appreciates it, but it's not. There's really only sort of a glimmer of understanding of what might be possible if we can reach some of these milestones. So I always like to look back and think about how science, and particular this field, shows up in the media. And one way to do that is to use the Google Trends search to put in a phrase, and you look, for example, at just different spikes. So this is going back, I guess, to 2004. You see a few spikes here. So this one was in 2008, 2006, maybe, where there was some announcement about how a quantum computer could solve Sudoku puzzles. And then there was a very confusing, or at least I believe that the author of this article that was very impactful, it kind of spread very fast, that a computer is a quantum computer could be 1 million times faster than a normal PC, but it was both faster and not faster at the same time. I guess that's what we call quantum speed up. And then a real conceivable breakthrough, this idea of quantum advantage or quantum supremacy, that was reported in 2008 and 19, I want to say. And this was basically finding some problem that Google claimed its quantum computer could solve, that would take an inordinate amount of time for the most powerful supercomputer that was classical. So actually, if you remove the word computer, you find that there's like a lot more of interest in quantum. And so if you just search for quantum, you'll find this interesting variation over time. I was interested in this. I downloaded the data and I did quantum Fourier transform, which is I took a Fourier transform of time of the word, the prevalence of the word quantum. And I thought this was kind of interesting because it's very much peaked. And then you, of course, could do a quantum inverse Fourier transform. It turns out that July is the least quantum month of the year. So I'm doing my best here to push the bottom of that curve up just a little bit. Yeah, so this is just some fun here. Okay, so this is a school, so I wanted to try to introduce some key concepts, what I believe are very important interlocking concepts, certainly that have sort of guided my own thinking over the last few decades. So we could start with a quantum computer. This is some construct that is able to speed up certain types of calculations. You need a quantum algorithm to get good quantum speed up. Quantum computers are made up of a number of quantum bits. These are two-level quantum mechanical systems that presumably have a lot of coherence. They're building block of the quantum memory of a quantum computer. And then you have quantum materials. So these, in some sense, have two roles, right? All quantum bits and quantum computers are made of, essentially, when you zoom in to the key aspects, they're quantum materials. And so they form the basis of all quantum bits. But there's also forms of quantum matter that we would like to understand. And so we may want to use a quantum computer to understand the properties of quantum materials, which are made of quantum bits. So there's this, deep connection between these three different concepts. And of course, at the center of all of this is the Schrödinger equation, that governs the quantum evolution of all of these systems. So you might be wondering, if you look at the news, Google Trends, and so forth, don't we already have quantum computers? Well, you could say like we do and we don't at the same time. We certainly have very beautiful pictures of monolithic structures that were made from advertising firms, and they look really impressive. However, if you look at the specs, if you look at what they're actually able to do, first of all, they're working with a relatively small number of qubits, quantum bits. They don't have error correction, which is extremely important for real scalable quantum computations. And really, there isn't a single platform that has yet emerged that has sort of brushed aside all of the competing efforts. So here you're looking at a superconducting based quantum computer inside of a dilution refrigerator. Here it's ion traps that are arranged above some surface. And they are competing platforms. They operate in a very different way, but they all have qubits. But again, as I said, we're at the beginning, and we're just trying to figure things out. This is, a quantum odyssey, if you will. If any of you have read Arthur C. Clarke's 2001: A Space Odyssey, this is the quantum version of that. So if we think about like what does it mean? So that this was an iconic sort of scene from the beginning of that movie, where the apes touch this monolith, and then like something happens, and they get sort of transform into humans. So the question is like, have we touched the monolith yet? I would argue no. We're close, but we're not there yet. And what I would argue is sort of what is the one milestone that I think would certainly demonstrate that we have crossed that threshold. And it's something that sounds really simple, but it's not. So if we imagine taking like the very simplest Hamiltonian, it's probably so simple you've never even been asked to do this as a homework problem in your quantum mechanics course. So you take a single qubit, so it's a 2-level system, and you simulate or ask, what is if the Hamiltonian were h equals 0? So that's kind of like, what does that mean, h equals 0? Well, if you look at the Schrödinger equation, this is the Schrödinger equation, and h is equal to 0, then d psi dt is equal to 0. That means that the wave function is unchanging with time, which means that if you are initially in a superposition of the 0 and 1 state, you will remain in that state for all time. So this is the simplest possible quantum computer because there's only one qubit. I mean, you could say a 0-qubit quantum computer, but that's maybe too trivial. But it's the simplest possible quantum computer with one qubit, the simplest, smallest conceivable memory. And you can also think of this as a material, right? Materials have a Hamiltonian that govern its dynamics. Nothing could be simpler than h equals 0. And so everything seems really simple and sort of trivial, and yet there is no technology that can do this. There is none of them, whether it's superconductors or ion traps or silicon spin, none of them are able to do this very simple, seemingly simple task. So, again, we're at the beginning. I'm patient, right? And you can probably afford to be more patient. So what I want to do now is sort of give you, again, take a step back, but maybe more from a personal perspective and talk about my own approach to science, quantum science and technology. So my quantum origin story was actually started back in 1999. I don't, maybe, many of you were not around then or very young, but what people were really worried about back then was not quantum computers, but rather the Y2K problem. So Y2K was year 2000, right? When all the clocks turn over from 99 to 00, it was predicted to to produce havoc because nobody thought that computers would last that long. I don't know, but it was a big computer bug, sort of worldwide, and of course this is one of the more sedate headlines. Yeah, so if in sort of a cartoonish sense, I was haunted by this, and so I decided to address the Y10K problem, which is quantum computing. So was interested in more long-term things, and for me a very pivotal moment was listening to a lecture that was given by Peter Shor. So he, if you sort of may recognize his name, he was inventor of very important quantum algorithm for factoring large numbers. And so 15 is equal to 3 times 5. That's a small number that could be factored, but he showed that a quantum computer could be have exponential speed up in this process if you could build one. And so I was, and at the end of his talk was quite abstract, but at the end, he said, "Oh yeah, maybe silicon spins could do this," and he pointed to a paper which I immediately looked up, and I became very interested in this. And at the same time, there were funding opportunities. So the next year, I was giving a talk with this title, Quantum Information Processing with Ferroelectrically Coupled Germanium Silicon Quantum Dots. I was actually working with ferroelectric materials, and I knew something about spins and sort of smashed them together. My audience was very polite, but this was a time like nobody knew anything about quantum computing. So it was kind of a little bit ahead of its time, but there were there were funding opportunities. As I said, there was a program called QUIST, which is Quantum Information and Science Technology. And again, I was introducing ferroelectric materials with silicon, germanium, and trapping single electrons in their spin on quantum dots and modulating exchange interactions and so forth. So this was a very exciting time, and I got very interested in this sort of general field. I also, this is, if you're interested in understanding how quantum materials impact or sort of impact or intersect with quantum computation, this is a theme issue that I co-edited with the Jim Eckstein a few years ago. And so one of the things that's really nice is that you can have so many different physical systems, and then you identify a 2-level quantum mechanical system from those, and then there's so many analogies that you can make and sort of mappings from one material to another material. So it's very interesting, also from a point of view of physics, right? The sort of universality that is manifest within the approach to building quantum computers. So in some sense, this experience, it colored my viewpoint and how I approach the science and technology frontier in the quantum space. So if I go to a conference or a workshop and I am introduced or exposed to a new quantum material, I I sort of have a flow chart that I asked, well, okay, maybe, is it a qubit? Is there a two-level quantum mechanical system embedded inside of that material? If not, well, maybe it has some property that could be really useful in developing a quantum computer, or maybe it can be used for quantum simulation, or maybe it's just a new state of quantum matter. If the answers to all these questions is no, then I'm probably a little bit less interested in those material systems. My research trajectory has sort of hummed along for many years, as it did after this transformative experience listening to Peter Shor. But there was another phase transition that happened in 2006 I want to tell you about. So in 2006, you may remember, of course, that was one of the years of the World Cup. And in 2006, it was in Germany. And I was invited to give a talk at a conference. The conference organizer was very interested himself in the World Cup, so he decided to hold it during the World Cup. This is actually, if you see, this is like a stairway. This is literally like a house or a little room. So the whole country, Germany, was turned into a big soccer ball. So it turned out that I asked my brother to get me, if he could get me a ticket, and he did, but he was too successful in the sense that he got me a ticket to the final. All right, this is literally a ticket, my ticket to the final of the World Cup. But it presented a problem for me. And the problem was that, as you know, the World Cup is a month-long event, and the conference was organized in the first half of the World Cup, the sort of group stage. And so there was a really long gap between the end of the conference and the final, so like 10 days or so. So I asked a friend of mine, who did he think that I might be able to approach to give some talks in Europe, because this is all kind of government-sponsored research, and I need to be able to do something during the day while I'm, at night I go into one of the beer gardens and watch games in preparation for the final. So I strung together a bunch of talks in Germany, Netherlands, and so forth. And one of the places that I went to was the University of Augsburg. And in Augsburg, there's a group of Jochen Manhart, and they had not published this paper yet, but they told me about the result, which was really interesting. So basically, they were looking at complex oxide heterostructures. In this case, there's a thin layer of lanthanum aluminate, which is a wideband insulator grown on strontium titanate. And what they found was that depending on how many unit cells of this lanthanum aluminate, the interface of the strontium titanate near the lanthanum aluminate would either be insulating or conducting. And it was a very sharp transition. So with 3 unit cells, the interface was insulating, and if you put one more, it became a conductor. So, and then if you took that 3 unit cell sample and you applied a voltage to the back of the substrate, you could switch the interface between the conducting and insulating state. So if you put 100 volts across the back of this substrate, you could switch. So this 100-volt pulse would switch the interface to a conductive state, and it would remain conducting when you turn off the voltage. And if you wanted to switch it back to the insulating state, you just change the sign of the voltage, and it becomes an insulator. So this, to me, was actually one of the. It wasn't like figure 1. It was, figure 3 or 4. It wasn't the most central part, but for me, it was really interesting. However, because this backgate was a millimeter away from the interface, it's really a length scale that made it too big to be kind of interest. It's not really nanoscale, but it was an interesting effect. So okay, I went to the final, right? But I must say I was a little bit distracted, and I think the referees even missed some of the plays as well. But I was really found myself thinking about other things. Although I should have been just watching the game, but I was really asking myself, was it possible to switch this interface between insulating and conducting on a local scale? And so I did come up with an idea for doing this, which is based on a toy that I played with as a child. I don't know whether this is a toy that you have or played with, but it's called Etch-a-Sketch. It's basically in the drawer, some back drawer of every child, pretty much until recently. And now I guess there's an app for that, but it's really not the same thing. So an Etch-a-Sketch, if you were to take it apart, and I don't recommend that you do because there's this fine aluminum powder, it's probably not good for you. What you find is that there's a plastic sheet here, and the aluminum powder sticks to the inside of that sheet, and then you can etch away or scrape off the aluminum by moving the stylus in the vertical and horizontal direction. So you can see these two bars here, and if you turn these knobs, you can move this horizontally. And if you're really good, which I'm not, you can make nice drawings, the line art. And then if you turn it upside down and shake it, the aluminum powder comes back. So it's a rewritable, actually it's millimeter scale. This is not how they advertise it, but it's millimeter scale control of the metal insulator transition, right? Because the smallest feature is about 1 millimeter, and the aluminum powder is presumably conductive, and then when you scrape away, it's insulating. So you can go back and forth on a millimeter scale. So we were interested in doing, kind of using this as an analogy. We use an atomic force microscope that has a very sharp conductive AFM, atomic force microscope tips. And so the features that we create are trillion times smaller in area than the Etch-a-Sketch. And so the description of how this works is that we work with this critical thickness of 3-unit cells of the lanthanum aluminate, and then we first make contact to the interface and put metal there, because this red region is highly insulating. So we need to punch through into the conductive area, potentially conductive area. Then we use this AFM tip and we sketch with a voltage, just like before, except it's a smaller voltage and it's being applied to the top. And what this is doing is putting protons on the surface. And those protons, those positive charges, attract electrons to the interface, but only where you pass by with a positive voltage. And so you can sketch different types of structures by moving around in a given pattern. You can also erase the structures. It's like turning it upside down locally by changing the sign of the voltage. You can create barriers and so forth, and you can use this to create a wide variety of nanostructures. And it turns out that these nanostructures at room temperature are extremely small. So what we demonstrated back in 2009 is that if you write a line and you measure its conductance, and then you move across the line and try to erase it, and you measure the conductance as a function of position, it switches from being a conductor to an insulator when the tip moves only 2 nanometers. And so that gives us a measure of the width of these nanowires. So they can be as small as 2 nanometers, which is only 5-unit cells of the underlying lattice constant of the material. So this is extreme nanoscale control of the metal insulator transition. And what we realized very quickly was that it was, there was a lot of potential there. And really, the potential was not just because we were making small things, but because the material itself, this underlying material, strontium titanate, is a very rich physical system. It has a lot of rich properties that are tuned by this type of doping that is achieved with the AFM. And so it's really the combination of the two that makes it extremely powerful. So I want to sort of give you a very quick kind of journey through what we have done, but focus on a few things that were of interest to us. And again, it's sort of colored by this question, right? We have all these questions about, what is this system? What could it be used for? And so for us, that's sort of curiosity driven. So we've written a lot of papers, probably about 50 papers since then, on various topics, from making sort of nano devices at room temperature to like terahertz spectroscopy, integrating with graphene, making ballistic nanostructures, investigating properties of superconductivity and quantum transport and so forth. And what sort of emerged from this is that there's sort of the beginnings of a new field, if you will, which is not coming from nowhere, but rather coming at the increased overlap between two well-established fields. So we call this correlated nanoelectronics, which is the sort of the mashup of correlated oxide electronics, which is responsible for developing materials like high temperature superconductors, and combining this sort of very broad family of materials with the paradigm of semiconductor nanoelectronics, where you can make, ballistic coherent devices that control single electrons and their spin and are, closely related to the nanoelectronics that are in your phones. So we want to combine these two very different fields, but we want to do them in interesting ways. And so we're looking for new effects that come only from the intersection of these two fields. So what we realize is that you can sort of think about this in a perturbative sense, like intellectual perturbation theory, where you say, okay, I suppose I have some device here. What happens if I swap out the material that people normally use, like gallium arsenide or graphene? You could also go in the opposite direction and say, hey, I don't understand why this cube floats. I don't understand, the mechanisms of unconventional superconductivity. And maybe there are sort of non-perturbative regime as well. So I actually want to give you some examples of all of these. And I want to start with this sort of investigation of superconductivity in this material. So it turns out that one of the many properties of strontium titanate is that it's a superconductor. So this is really basically a paper that we published in 2015. But the story really begins in 1964, where the phenomena of superconductivity in a dilute semiconductor was first discovered. This is a really surprising thing, that you can have so few carriers in a material and yet it becomes superconducting. And in fact, the first superconducting dome was reported in this material. This is 20 years before high temperature cuprate superconductors, which also have this non-monotonic TC versus doping. More recently, with these oxide interfaces, it was sort of rediscovered or reinvigorated this investigation of superconductivity, because now you can dope the system electrostatically rather than just chemically. People have observed superconducting domes that were tuned not by changing the doping density, but by changing the gate voltage. So we were interested in the general phenomena of superconductivity, but we were also want to make nanoscale devices. So we were interested in this particular type of device, which is called a single electron transistor. And it's made from these 5 nanometer wide nanowires, tunnel barriers, and gates, and so forth. So the way that this is a school, so I'll go into a little bit of detail about how a single electron transistor works. Basically, this is sort of the abstract picture. You have some island here, a quantum dot, QD, and it's very close to source and drain leads. So electrons can tunnel from a source drain into this island and into the dot, but only if there's available energy, right? So this, because it's a quantum dot, it has discrete steps of, so there may be occupied states and unoccupied states of this quantum dot. And as you change the chemical potential in the quantum dot with the gate, you can fill up these states. And every time you cross one of these states, you find that there's resonant conduction between source and drain, because there's no, at that crossing point, there's no energy required to put the electron onto the quantum dot and then to take it off again. So you get a spike in the conductance every time you reach a new addition energy for the quantum dot. And so so this produces resonant tunneling. And then in the middle of that range, for example, over here, the chemical potential of the source and drain are in between the occupied and unoccupied states. So in order for an electron to go between the source and the drain, it has to find energy. It has to get energy from somewhere, and if it doesn't have energy, there's a blockade. So in this regime, there's no tunneling, and so the conductance is zero. But if you were to put a chemical potential difference, then it would be possible for this electron to hop onto the lower energy state, and now this is unoccupied, and an electron from the drain can go over here and so forth. So the general structure or features, if this is the vertical axis, is the source drain bias, and the horizontal axis is the gate bias, what you find is that there are sort of insulating regimes and conducting regimes. So the insulating regimes are the white regions here, these diamond features, and then the intersections points are where you go from n-1 to n+1 electrons. So the other thing that can happen is that a magnetic field can Zeeman split the energy states, and so that will cause a shifting of these levels up and down, and it will impact the shape of this structure by moving these points to the left or to the right. So this one would move, let's say, to the left, this one would move to the right. It would cause the diamonds to grow and shrink in size, but you wouldn't see, for example, a change in the number of intersection points. And you can trace these points as a function of magnetic field. So this is a single electron transistor created from this oxide interface. This is typical data, and you can see these diamonds, right? So this is, again, the source drain bias and the gate bias. There's actually a superconducting regime here. These measurements were made at 50 millikelvin in a dilution refrigerator. And what I want to do is I want to focus on one of these diamonds. So this is a zero magnetic field, and I'm going to increase the magnetic field 1 Tesla at a time. So if I go 0 Tesla, 1 Tesla, 2 Tesla, there are some subtle differences, but it's not that remarkable. But now I'm going to go to 3 Tesla. And what you'll see is that actually there's a new diamond forming between the big diamonds. And if that doesn't seem very apparent, I'll go to 4 Tesla, where now you see that they're all about equally spaced. And this is a very strange thing because the number of diamonds has doubled, right? So here is, again, the 0, 1, 2, 3, 4. If you take a cross section through 0 bias, you see that the single peaks persist up to 2 Tesla, and then they start to split. And so it took us some time to understand what this was, but really we had to reinterpret these diagrams because we believe now that these are stable states of pairs of electrons, not single electrons. And they break apart, in this case, at 2 Tesla. So another way to see this is to make an intensity plot of the zero bias conductance as a function of magnetic field along the vertical axis and the gate voltage along the horizontal axis. And the dark regions are the blockaded regions, and the bright green yellow regions are the places where you have conduction. And the assignments are that this is a state in which there are n - 2 electrons in the island, and then it jumps into n, and then n+2. So instead of going n - n-2, n-1, and so forth, it jumps by 2 at a time. If you were to apply a sufficiently larger magnetic field, then you could get to a regime where there was n-1 or n+1. And so this is a critical field at which the electron pairs break up. And it turns out that electron pairing is an ingredient in superconductivity. So you need, of course, phase coherence between the electron pairs, and it's a macroscopic quantum state. But what we established, and in fact, that superconductivity happens at a much smaller magnitude of the magnetic field. So the superconductivity gets destroyed at maybe 0.1 Tesla, but this persists from 0.1 Tesla to 2 Tesla. So this is an example of electron pairing without superconductivity, which was first predicted in 1969 in response to the discovery of superconductivity in strontium titanate. So it turns out that, yeah, this pairing field can be much larger than the upper critical field. Pairing temperature is also about an order of magnitude higher. And so we think that there's now this new phase of matter, which is in between the superconducting state and the normal state. So these are sort of not really scientific depictions, but normal state, right? Every electron is doing its own thing. And here the pairs are coherent. So the idea of the paired non-superconducting state is that there's this binding of electrons due to some attraction, but the pairs themselves are not phase coherent, and so you don't see superconductivity. Okay, so now I want to show another example, sort of moving in the opposite direction, where we take a device, let's say, from the paradigm of mesoscopic transport and ask what happens if we swap out the materials. And I want to go right to a very unusual phase, but kind of talk about this in conjunction with something that we discovered a few years prior to this. So it turns out that not only can electrons pair together, but you can actually have even higher groupings of bound states of electrons. And what you're seeing here is this quantum wire or electron waveguide in which there are 3 modes of conduction, one of which involves single electrons, and the other one involves electron pairs, like what you'd seen before. Now, these are in an open system. And then on top of that, you have a trion phase where there are 3 electrons that are moving. Each one of, so the single electron contributes to the conduction according to the conduction quantum of E²/h. So the first one, the lowest energy mode of conduction, gives you E²/h, and then you add 2 more to get the pairs, and then you add 3 more to get the trion. So it turns out that there's a whole stack of these phases where the conduction follows a sequence that corresponds to Pascal's triangle. So yeah, so this is sort of Pascal's triangle. You may have made this kind of number triangle as a child, where the next generation is the sum of the 2 previous ones, and so forth. So you get very interesting, binomial distributions. There's a lot of interesting features. It turns out that the diagonals of these are relevant to quantum transport in various dimensions. But most conductors are not ballistic. So all the things that I was telling you about before relate to ballistic transport, where electrons don't scatter, but most of the time in most materials, electrons travel for a certain distance and then they scatter, maybe off of a phonon or impurity, and that gives a conductance which may depend on various quantities, but generally leads to the relatively straightforward Ohm's law relationship. But in ballistic conductors, like the ones I'm going to be focusing on, you have channels of conduction, like lanes in a highway, and there's no scattering. You would think that maybe the conductance should be infinite, but it's not. It's actually constrained by this idea of Landauer quantization, and n here represents it's a number which depends on how many channels you have and what the charge is per channel. But so this is something that you generally get in one-dimensional or quasi-one-dimensional conductors. So what I was going to show you is that we actually get a new formula that comes from looking at a system in which there are two transverse degrees of freedom. So you have lateral and vertical degrees of freedom, and that enables a stacking of electrons in an increasing degeneracy. So at the top here, you see, again, E squared over H, and then the next row is 2E squared over H, and the next one is 3E squared over H, and so forth. So this is different from what happens in ordinary semiconductor quantum wires, where generally you just have confinement, a strong confinement in one direction, and then number of transverse modes in the lateral direction. So another way to think about the ballistic transport is to compare it with the way in which light propagates. Now, there are important differences, but basically, if we think about optical waveguides, you might be imagining optical fibers, for example, that have different modes of conduction, optical modes, like this is the TEM 0 mode, the Gaussian, and then you have different excited modes. And so the main difference is that these are electrons, they're fermions, not bosons, but the wave nature is really what's determining the ability to propagate through a system. And in the late 80s, the first example of this quantized conduction was discovered in something called a quantum point contact. So this is basically, you have a high mobility two-dimensional electron system in this entire rectangle, and then you pinch it off with these gates. So you constrain electrons to only travel through this narrow region from bottom to top. And depending on how many wavelengths of the electron are allowed to propagate in this transverse mode, you get a conduction that is quantized in units of E squared over H. And it's discrete. So what you find is that you get steps in the conduction. And these steps actually can be visualized if you have a scatterer, like from a low temperature AFM. This is beautiful work done by Bob Westerveld's group at Harvard, where they could actually image the lowest mode, which is, okay, it's a little noisy, but it's just like the Gaussian, and then there's the 2 lobes and the 3 lobes, right? So depending on how you tune the system, you can allow different numbers of transverse modes to pass through. So we're interested in creating one-dimensional electron waveguides. These are very elongated structures. And the way that we think about them is that you have free propagation along the wire, but the wire itself has subbands that are given by the quantum confinement in the lateral and vertical direction. And so you can think of the energy dispersion within these structures to be, parabolic as a function of k sub x. X is the propagation direction. In this case, the chemical potential is such that there's only one subband occupied, so just the lowest mode, but then you can tune it by changing the chemical potential so that now there are 3 modes, for example. And so you should get 3 times the conduction that you get over here. Each occupied subband gives rise to a conduction of E squared over H. So what you would see is that as a function of the energy or chemical potential, you would see these steps. And the bottoms of these subbands are when you jump from a lower conductance state to a higher conductance state, and that can also depend on magnetic field. So in order to understand, the basic way to understand this is to solve the Schrodinger equation and ask, where are these energy states? And so this is a problem that I think you all can probably solve. It's a problem in 3 dimensions where you have confinement. So these are the kinetic energy terms, and this is parabolic confinement. So it's basically a parabola. You get evenly spaced energy states. The only difference between the y direction, which is lateral, and the z direction, which is vertical, is that in the vertical direction, it's a half parabola. So it's basically a parabola that goes to infinity at the interface. But we know how to solve that. You just remove all the even states, and it's a trick that everybody does. And then you have magnetic field that couples to the vector potential and then to the spin. If you solve this, you get energies, eigenvalues, and eigenstates. These are the eigenstates. So these are like the waveguide modes. You can think of these as the cross section of the electrons as they're going through the page or the screen that you're looking at. And here there's no change in sign of the wave function. Here there's a node along the horizontal direction. There's a node in the vertical direction, and so forth. So these 2 numbers represent how many nodes of the wave function there are in the horizontal and vertical direction. And then there's a copy of these for spin up and for spin down. And the energies themselves will shift in a magnetic field. And this is a plot of each of these red lines represents the bottoms of those subbands as a function of magnetic field along the horizontal axis and chemical potential along the vertical axis. So I'm showing you this because we can actually measure this experimentally. What you see here, again, the bottom is the theory and the top is the experiment. So if we measure for one of these devices, as we change the gate voltage, the chemical potential, we see these plateaus. If we differentiate these curves, you get an intensity plot. So this red line here represents the transition between 0 and 1, and so forth. And so you can then take this curve, turn it into this one, and compare it with experiment, or usually the other way around. We adjust parameters like effective mass and so forth to match what we see experimentally. But the fact is that we can account for all of the lines that you see here, all of the subbands. So, for example, we could sit at a magnetic field of 7 Tesla and tune the chemical potential to this point. At this stage, we have a completely spin polarized, single component, one-dimensional electron liquid, right? There's only one type of electron with one spin and one spatial degree of freedom. But we can also go to other modes where there are mixed numbers of states as well. So again, getting back to this, some of the really weird things is this idea of Pascal phases. It turns out that under some conditions of these parameters, you can get crossings of these different modes. And when 2 modes cross, that means there's really no energy difference between them. And it's possible for actually electrons to lock together. Now, in this particular set of parameters, you notice that you have, well, any 2 lines will generally cross or not cross, but the possibility of having 3 lines cross or intersect, and then 4 lines and 5 lines, something really special has to happen. And that happens basically with one parameter experimental that you need to have in the material, and one parameter that comes from the magnetic field. So we're able to observe, in fact, a situation in which you have the crossing of 2 and 3 and 4 and so forth. And then you need to add something else, which is the attractive electron-electron interactions. And when that happens, these crossings turn into strips that have a finite width. And so what you're seeing here are these lines that are actually coming together and staying together over a range of magnetic fields. So those are stable states. And there is a sequence of them, which we can, we interpret in the following way. So if you start with the lowest energy situation, you have 0 conduction. It's like the vacuum state. There are no electrons propagating in the system. And then as you increase the energy, you can get to a point where now there's just a single type of electron going through, spin polarized, and then you can increase more. And now, in addition to the single electrons, you have pairs of electrons, and they're propagating through. So the conduction is 1 plus 2, which is 3. And then you can continue and go and add the next state, which is a trion phase. And now you have 1 plus 2 plus 3, which is 6, and it actually continues. So this is a very unusual state of electronic matter that was discovered by this exploration. So going forward, what we're interested in doing is synthesizing new forms of quantum matter. I see it's almost 9, so I'm going to go a little bit faster. Basically, this is where we're going, right? We want to create new forms of quantum matter by sort of bottom-up control of this metal insulator transition, and then sort of build up materials electronically, and then explore their properties and hopefully design them in the future. So it's very similar to the idea that Richard Feynman had conceived of. So we want to start with some initial state and then manipulate it and produce some new form of quantum matter. So one of the things that we did recently was form a Kronig penny model. So we start with a quantum wire, and then we modulate it with a period of about 10 nanometers. And what that ends up doing is creating a whole bunch of electronic subbands. And those subbands end up fracturing the electronic bands that you saw previously. Now there's a whole manifold of them that show up, and you get fractional conductances. It's complicated because of the electron interaction. We can also engineer spin orbit interactions, and we do this by causing a meandering of the wires just by moving the tip back and forth. That acceleration as the electrons move back and forth engineers a periodic spin orbit interaction, which also modifies the electronic band structure in a fundamental way. One of the things that we're doing right now, this is a sort of active program, is to integrate these materials with other systems like two-dimensional van der Waals layers, like graphene, bilayer graphene, ruthenium chloride. And so the idea is to imprint electrostatically new interactions on interesting and existing materials. And so, so to sort of take a step back and think about like where we are right now versus when this started. Is this material a new state of matter? I would say yes and yes. Sort of two examples, right? The existence of electron pairing and the Pascal states. These are new phases of matter that were discovered or created. Can it be used for quantum simulation? I would say yes. We've been focusing so far on one-dimensional systems, these Kronig penny and serpentine superlattices, but we are now expanding into two-dimensional systems. And then, the question is, well, how does this impact quantum computing, the field of quantum computing, and so forth? I would say this is still an open question. We do have efforts to develop new quantum bits, but they're in the early phases of our efforts. And of course, they have to compete with existing platforms. So let me just give credit to many collaborators. Patrick Urban is a research faculty, works very closely with me, and these are some theory collaborators, David Pecker, Roger Mong, and their students who've since graduated. I also work very closely with people who grow materials, in particular Changbaum Ohm at the University of Wisconsin, Madison. He provides all of the oxide materials. And this is another theory collaboration. And then Philip Kim is also collaborating with the graphene-based devices, and Alex Sinitsky with graphene nanoribbons. This is a snapshot of my research group from a couple of years ago. And these are the funding sources of support. This is a recent picture from my group. So thank you for your attention.
Thank you for this very nice, exciting, and comprehensive talk. That was a pleasure to listen to.
It's my pleasure.
Can we now take some questions?
I'm happy to try to answer questions.
Yes, sure. Please, please ask questions using microphone or chat button. So in chat we have questions. Jeremy, can you read messages in
Oh,
the chat?
yeah. Hold on 1 second. Now I'm opening that up. Yes. So I see one question. Does strain-induced bending affect your Pascal states along oxide nanowire? That's a really good question. So the Pascal experiments are done at millikelvin temperatures. And so in order to answer that question, you need to strain or bend the materials at millikelvin temperatures. Now that said, we actually have the ability to do that. This is something that we recognized many years ago, that strain can have a profound influence on many properties of these complex oxides. It can induce ferroelectricity at room temperature in strontium titanate, which otherwise would not be ferroelectric at any temperature. And we do believe that the changes in strain will impact not only the effective mass of the carriers, but will probably affect the pairing energies and so forth. So I would say that this is a question. So we have a strain cell that works at millikelvin temperatures. We're doing an experiment now. My student is doing an experiment where we draw nanowires, cool them down to millikelvin temperatures. I say we, but she's the one who's doing it. And then straining along one direction. And then asking the question, well, is it still superconducting? Is this something suddenly happen? It turns out that when you start pulling on the material, there's a point where it suddenly stops being a superconductor. So it's superconducting, then suddenly it's no longer a superconductor. And then if you relax it back, it goes back to being a superconductor. So we think these are important experiments because they provide insight into the mechanism of superconductivity. Why is it that the electrons are attracted to one another? So the Pascal states, we've not done an experiment in the Pascal regime yet, but this is definitely something that we're interested in. Understanding, like, can we pull apart or change the stability of a trion phase? Or can we induce it? What is the phase diagram, not only as a function of magnetic field and chemical potential, but now we've introduced a new axis, the strain axis. So these are really important questions.
Okay, thank you. More question, please. One can also use the microphone if needed.
I do see another question. So it's not directly to, you mentioned the quantum Fourier transform. So yeah, so the quantum Fourier transform that I was talking about was like quantum with air quotes, Fourier transform. So I was taking a Fourier transform of the frequency of the word quantum, which is a play on very important quantum algorithm that was developed by Peter Shor, which involves using a quantum Fourier transform to as part of the factoring of large numbers. So the quantum Fourier transform, which is a quantum logic gate sequence that was developed by Peter Shor is probably the most central construct in that quantum algorithm. But yeah, I didn't really, I didn't cover the quantum Fourier transform itself. I do remember struggling to listen to his initial description of it back in 1999 when he first started. I quickly locked in to the experimental realization, thinking that that was something that I could address more effectively. But it's you know, there are many, I would say, there are now many educational tools that are available to go through the quantum Fourier transform and Shor's algorithm. And I would probably recommend like the IBM Qiskit and so forth. They have a bunch of lectures that can help you work through this important algorithm. Okay, so another question. I missed the part, I guess. VSG is the source gate voltage. VSG, yeah, there are a lot of symbols. I apologize. So there are, there's generally in these three terminal devices, there's a source, a drain, and a gate. And let me see if I can find a picture of one of them. So maybe this is the close enough, but basically, so VSD is the source drain bias, right? Here, VSD. So that's basically the energy difference between the source and the drain. And then there's a gate. So if something has a G, so VSG actually in our nomenclature refers to this a side gate, because we also have a back gate. So we call that VBG. It's not a standard thing, but we have different types of gates. And normally the ones that we work with are this side gate because it's kind of on the same plane as the actual source and drain and so forth. But generally the side gate is what tunes the chemical potential in our experiments. So for example, here, right? Here we have magnetic field, and then we have the side gate, which tunes. You notice that as you increase the side gate, you go from having n-2 electrons to n+2 electrons. And that's also true with the electron waveguide devices. So, for example, here. So actually, you can see on the bottom, you write mu, which is chemical potential. On the top, we have VSG. So there's a relationship, a linear relationship between VSG and mu, which is called a lever arm, and we can perform experiments that tell us that ratio.
Thank you. More question? Any other question? Yes.
Okay, I see another question. When you apply strain, you spontaneously lose superconductivity. When you remove it, the system turns back to the superconducting state. How fast is this transition? That's a good question. Yeah, so there is a limit to the speed with which we can change the strain state. So it turns out that there are piezoelectric transducers that we have to energize, and when they energize, they heat up. So if we try to change it too rapidly, the whole system warms up. And so we are not able to quickly change the strain state. the second question is, or maybe the main question is, is there hysteresis? There does seem to be some hysteresis. So we believe that the strain state alters the sort of buckling of the unit cell. So it actually has the unit cell is not isotropic cubic at low temperatures. It elongates along one direction, and then that direction can be out of plane or in plane, and you can have domain walls that separate them. And there's a 0.1% difference in the unit cell length. And so this is associated with other effects like giant piezoelectricity and so forth. We think that those domain walls play a very important role in mediating superconductivity. So what we believe is that when you push on a sample, you remove all these domain walls and you remove the mechanism of superconductivity, and suddenly it goes away. And then if you relax the system, the domain walls come back. This is a hypothesis that we're trying to explore to see if that's actually correct.
Yes. So thanks a lot again. So it seems that no more questions. So if no more questions and you don't mind, Jeremy, perhaps we can stop here.
Yeah, like I said, I'm very delighted to give this talk, and only regret is not being able to join in person.
But this is a future issue. So we were very happy to have you with us. That was very exciting talk indeed. So we'll see to meet in person. Thank you so much for coming and joining us.
Thank you. My pleasure. It's my pleasure.
So bye.
Okay.